Suppose we have a function f of xy defined on some region D of the xy plane. So I'll just sketch a quick picture here. Say we have, again, our region D could be anything, but it's some bounded region. So here's our region D in the xy plane. And the function, of course, assigns a height to every point on this, in this region D. So the function f maps the region D up to the surface, and we'll call this surface, so call the surface S, but the surface here is given by the graph of the function f on the domain D. What we want to do in this lecture is we want to try to write down an integral for the surface area of this surface determined by the graph of the function f. So that's our question, what's the surface area? And as usual in calculus, especially calculus 3 now, the surface area of the surface, which we'll call S, it's a little confusing, but this S is the surface area of the surface, is going to be the double integral over the domain D in the base down here, domain D in the domain space, of whatever the surface area element is, ds. Okay? And if we want to be able to compute this and actually find a surface area for this surface, we need to figure out a formula for ds. So how can we represent ds? Now, to do this, you probably won't be surprised that we're going to chop our domain up into small rectangular pieces. And so I'm not going to go through the whole Riemann sum argument here, but what I am going to do is say, okay, if we chop this up into small pieces, so we partition the intervals in the x direction and the y direction, and we find these small rectangles, let's just look at one rectangle and try to figure out what the delta Sij is here. So this is the very small piece of surface area, which when we take a limit will become ds. So this is for a rectangle Rij. And again, I'm not going to work through all the details, but here's what it looks like. When this f gets mapped up to the surface, you get a kind of warped, curved rectangle up here. And so I've drawn the y direction as blue. So what we're going to do is zoom in on this picture, try to get a formula that we can then, in our minds, take a limit of and get an integral formula for. So again, this little box, so I'll draw the whole thing out. So we've got, in our domain space, we've got a nice rectangle. This is Rij, pretend everything's parallel here. Rij, and f, when this maps this up to the surface, this becomes slightly curved. So in particular, these two edges might not be perfectly rectangular anymore. Remember, this piece is curving in three-dimensional space, not just in two-dimensional space. So what we want to do is try to approximate. By the way, we'll say, let's just fix this point right here, call this point P, and then this point over here is P, f of P. What we want to try to do is approximate the surface area, the area of this piece of the surface. And one way that we can do that is by approximating these curved portions that emanate from P, f of P, approximate these portions by portions of the tangent plane. So in particular, we can think about a small piece of the tangent plane in this direction. I'm going to write this in vector notation, call that one u. And then also a small piece in this direction, call this one v. And again, the u is in the direction of the x-axis, v is in the direction of the y-axis, but these two vectors, if we think back to our study of vectors, these two vectors will fill out a parallelogram in space. Okay, so these span a parallelogram, and everything's supposed to be parallel here, so you might have to modify my drawing. I'm not the best sketcher in the world, as we all know. But what we can do then is, if we can compute the area of this parallelogram, we can say that the area of this little portion of the surface, so the surface over Ij, is approximately equal to the area of the tangent plane over Ij. And so I'm just making up notation here, but this one is the surface. This is what we want. We want to know the area of the surface, and this one is the tangent plane. So a plane is easier to understand geometrically, especially if we have some vectors that describe the little portion of the plane that we're looking at. So that's what we're going to do now. Compute the area of this small piece of this parallelogram, this small parallelogram piece of the tangent plane, I should say. And once we compute that area, we'll say that's approximately the surface area, take a few limits, and we'll have an integral. So the first thing we need to do then, the next thing we need to do, is write down some formulas for these vectors. So let's assume that the vector is changing in the x direction, that we have a tiny dx, or delta x in this case, so a tiny change in x, all right, and a tiny change in y. And so these two changes in x and y are independent of one another, but for each of these, the change in z is not independent, right? And so we talked about this when we talked about differentials, but the change in z of the tangent plane, this delta z, if we're fixed in the y direction here, this change is just equal to df dy at this point P times delta y. So that's the differential in the x direction. And so that tells us then that our vector v, so I've done y first because it was easier to draw for me, but our vector v has components. 0, it's not changing in the x direction at all. Delta y in the y direction, it's changing a little tiny bit in the y direction, just a tiny change. Remember, these are supposed to be very, very small changes. And then the change in z for this vector is given by df dy at the point, but let's just leave it as df dy times delta y. Okay? We then can look at x, the vector u, which is in the x direction, and this is exactly the same situation. This tiny change here, delta z, this one's given by df dx in this case at the point P times delta x. And again, we assume that we have a small change, delta x, in the x direction. And so our vector u is given by delta x change in the x direction, 0 in the y direction, it's parallel to the x-axis over here, and then the change in the z direction is df dx times delta x. Okay, so these are the two vectors that make up our very small parallelogram, which is a subset portion of the tangent plane, and we want to find the area of this parallelogram. And at this point, you might remember that the area of a parallelogram that's built by two vectors like this is just the length of the cross product. Okay, so the area, our surface area element, our delta SI, this very small change in the surface area, this is going to be equal to the length of the cross product of these vectors, u cross v, or v cross u. I've got it written as v cross u. Remember, the length doesn't depend on the order. So let's do it as v cross u because I've already got it written out, stacked up this way, so it'll be easier to take the cross product. And so this will, of course, be the length of the vector. So if you look at these vectors, the cross product, the first component is the df dx times delta x, delta y. The second component is negative, so that's going to be this one. So df dy times delta x, delta y. And the third component is going to be negative delta x, delta y, the way I've got it written here. All right, but we're taking a length here, and because we're taking a length, we can actually factor out, there's this term, delta x, delta y, shows up in every single entry, and so the length of this thing is going to be, I'll factor the delta x, delta y out to the side here, and then the length of this will be the sum of the square root of the sum of each entry squared. This entry right here is a -1 actually, because we factored this out, right? And so I'm going to rearrange the order a little bit, put this 1 in front. It's going to be 1 plus derivative df dx squared at the point, of course, plus derivative df dy squared, and then times this element right here. Okay? So this is the key argument here for computing the area of the tiny piece of the surface area. This is, again, of the tangent plane. We're approximating the surface area by the tangent plane. And so let's go on to the next page and review this. We've got that our delta S, change in surface area, we just computed that this is equal to 1 plus the derivative in the x direction squared plus derivative in the y direction squared for this function times delta x, delta y. All right, we did this all in rectangular coordinates, but this could just be wrapped up into a delta A. It's a change in the area of the small rectangle in the domain space. Okay, And so when we take the limits, so here we're calling in Riemann sum, which I'm not going to write this argument out, but if we were to take a Riemann sum and call in some limits here, then this would tell us that the infinitesimal change in the surface area is exactly the same portion here, 1 plus dxf squared plus dyf squared times dA, and therefore the total surface area of the surface is equal to the double integral over the domain. We have to add all these up. So we computed this for one tiny rectangle. We take the limit, we add them all up, right? And so this surface area is then given by this double integral. 1 plus, again, I'll keep using this notation, dxf squared plus dyf squared integrated over the entire domain with respect to area, dA. So this is our surface area integral when our surface is given by the graph of a function.